Buenos dias, amigos geometría. Good morning, geometry friends. I was perusing my book. I have a hard copy of this and a PDF copy, both. Frank Morgan's Reminding Geometry Beginner's Guide. And I got to this section. Hello. Hello. Here it is. 69. Okay. And the Gauss-Bonnet Theorem. Is there anything not named after Gauss? Okay, this is confusing for me, and he does a lot uh, of theorems and proofs, which for me is not good. I need to do problems. I need to do examples. So that's what we're going to do to try to understand what this rascal is. Okay, the example I'm going to use to help me understand this theorem is remember that we did a couple of videos on geodesics. I'll leave a link in the description. So we have a point on a sphere, and the angle from the North Pole down is theta. The angle around the equator is phi. Okay. And what we did was we defined a tangent vector at that point, a unit tangent to vector that now that's in a plane on the surface, right? So this is a unit tangent vector on the plane on the surface. And when we move that down to a geodesic, which is a great circle like this, and we moved it all the way around, you see that it stays completely parallel to itself. So that's a geodesic. When the covariant derivative of the vector components are zero, that's a geodesic. But if we move it up, let me put it, I think here, there's 45 degrees. And we move it, you see that it's when it comes back around, it's at a totally different place. Okay? So what I'm going to do is use that theorem to try to understand the difference between those two. So I'm going to take a snapshot of that vector when it's at phi equals 0, and then when it's at phi equals 360. So it went all the way around. So using that Gauss-Bonnet, the theorem, I can calculate this angle between the starting point and the ending the point. That's what I'm going to try to do. Okay. So this study of parallel transporting vectors around the surfaces has a name, and it's called holonomy or holonomy. I've heard it said both ways. I like holonomy. It sounds like something I would have done in school. And as applied to the theorem, now this theorem applies to many things, okay? This is a pretty deep situation here. So if you're interested, you need to look this up and read about it. I am only interested in its application for parallel transport on a Riemannian surface, okay? So it's saying that that angle we looked at, a phi, they're calling it here, is the integral over the closed loop of the Gaussian curvature times the area of that loop. Okay. Now, here's what we had. So we have these. So the vector started here. This is a unit tangent to vector. And it's not on a geodesic. It's not on a geodesic. We looped it all the way around and it came back to there. So here's the difference between these two things. Okay, so how we're going to use that integral is like this. So we're going to say that the the phi goes from 0 to 2 pi, right? So we held the theta at 45 degrees, and then we changed phi all the way around by 2 pi or 360. And then the integral of this one is just 0 to pi. Okay, so we found in previous videos that the Gaussian, the curvature for a sphere is just 1 over r squared, right? And now this dA the part can be written as the volume element times the two infinitesimals. Now, I'm going to leave a link in the description of what is that thing. Okay, this is called the volume element, and it's the square root of the determinant of the metric, the tensor. Okay, I can't go into all of these details in this video. It'd be an hour long. I'll leave a link here. I'm sorry about all the links, but I don't like long videos, and I don't think most people do. Okay, so for the surface of a sphere, we found this many times. The metric tensor is, so this is E theta dot E theta. This is E phi dot E phi. So the determinant of that is just this times that. So we get this. The square root now is the volume element is just r squared sine squared the theta. So we can use that in this equation, and we get this. Okay, so here's K, here's the volume element, and here's our infinitesimals. And the r's to cancel, so we're just left with this. And so the integral of d phi from 0 to 2 pi is just 2 pi. Integral of sine is minus cosine. Then we take our limits. So we get a minus phi, and we get a negative times a negative is a positive cosine of 0. So we just get this equation, 2 pi 1 minus cosine of theta. And we said theta was 45 degrees. I held it constant, okay? So here's theta. We plug that in, and we get 105.44. Okay, so the Gauss-Bonnet theorem is telling me that when I tried to parallel transport that vector around this circle, which is not a geodesic, the difference between these two vectors here is 105 degrees. All right, so let's go look at that on the graph. Okay, so here's the original tangent, the vector, and I put it in its plane. So it has to stay tangent to this plane all the way, which is why it so drastically changes direction, see? Because it has to stay in that tangent plane. Whereas if we're on a geodesic like that, see, the tangent plane, it stays constant. All right, so let's go back to 45 because that's where we're doing our work. Let me get that tangent plane off here because it gums everything up. Okay, so we said that we want to take a snapshot of this when it's at phi equals 0 and phi equals the 360. So that's these two vectors. So here's T0 and T360. Okay. Now, the way we can find this angle just with vectors is we can take the product. So the cosine of this angle will equal the dot product of these two vectors divided by their magnitude. Well, their magnitudes are 1 because they're unit vectors, so we don't too care about that. Okay, so here's the product. So T0 is red, T360 is blue. Here's the product. We say the angle between them is equal to the inverse the cosine of the product, and there it is, 105.44. Why do I keep doing that? And here's what we got from the document, 105.44. So it works, and it met the initial and final conditions. Okay, so this is one way I can understand this theorem. The other ways having to do with topology and stuff, no, I don't. I might. All right, see you later.